So yesterday we introduced the idea of statistical inference, and we introduced two different ways of performing statistical inference models. We talked about classical maximum likelihood estimation, and then we talked about Bayesian statistics. And then in the third lecture, we talked about Markov chain Monte Carlo, which is a very common algorithm that allows us to fit Bayesian models to data, okay? So what I wanted to talk to you about today, though, is extending some of these ideas specifically to the types of epidemic model that you've spent a lot of time on in this course, principally things like SIR, SEIR models, okay, these compartmental models. And it turns out, as you might expect, because the models themselves are not simple, that it can cause us some challenges. So these models, the key challenge with many of these models is that we can't write down the likelihood function, okay? So our two approaches we talked about yesterday, maximum likelihood and Bayesian analysis, both require us to be able to write down a likelihood function, okay? And we saw a simulated example yesterday where I could write down a likelihood function because I simulated the data, okay? But in reality, the key problem is that most of the time, real data do not adhere to, are not the exact data that we need in order to fit our model, okay? So we have an additional step, which means that it's more difficult to calculate the likelihood, right? And that's really the big headache, whichever approach we choose. So I'm going to talk about that a little bit. What I just wanted to talk about is, we talked about this yesterday, so just a reminder that the process that we should undertake if we have data is we design a model, we fit that model to data, and then we should really do some kind of model checking, okay? And that is just to check that our model is doing a good job, all right? And that it can at least recreate the data that we've got. If our model fits don't fit well, then that suggests we might need a different model, okay? So, and this is true of any statistical model that you do. It's true of regression, and it's true here. But once we have a model, and we fitted it, and we've got parameter estimates, then we can use that model for different things. So we can use it for inference, so i.e. we can look at the parameter values and try to interpret them in some meaningful way. And we can generate uncertainty estimates either through confidence intervals or credible intervals, things like that. We can also use it for prediction, okay, which is essentially saying to predict what might happen if the same outbreak were to occur under the same conditions again and again, okay? And this is essentially what we do when we plug our parameter estimates in and we simulate from our model a load of times, right? And that gives you some information about the range or the behavior of that model under those same conditions. The other thing we sometimes use our model for is forecasting, okay? And this is the problem of extrapolating into the future, all right? So if you're doing, you know, for example, you're wanting to explore, you know, how you might implement a vaccine rollout policy or something like that, then that will typically be using forecasting, right? We can do all of these things once we have the model fitted and we have uncertainty about our parameter estimates. Yes?
So the COVID models that were published then, they were forecasting, not predicting, right?
So they were a bit of both, because what they tended to do, well, I can only speak for the UK models. So what they would do is they would fit the data to the data that they had. So they fit the model to the data that they had. And then they would do a sort of prediction. And then what they would do is then forecast into the future, right? So typically decisions during COVID were made on a particular day. So often the government would say on the Friday afternoon, we want you to explore this scenario and we want the results on our desk by Tuesday morning. And they would go away and do their forecasts, do their scenario planning, and then report. Yeah, so it was a bit, but what would, in that circumstance, what tended to happen is that those parameter estimates would be updated as more data came in. So it's what we would call real-time forecasting. So at the beginning, those forecasts have huge uncertainty because we don't know very much about the disease. We don't have, you know, our parameter estimates are very uncertain. as more data come in, we learn more about the parameters, we learn more about the trajectories, and so therefore our forecasts tend to be more reliable. The key thing to remember about forecasting is you just have to be, it's like any extrapolation. It's the same as if you extrapolate a linear regression model, right? When you extrapolate beyond the range of the data, you are assuming that the model is going to behave the same as you go forward in time, okay? And what that tends to mean is that forecasts are usually more robust the shorter they are. The further away from the data you go, the more likely you are to get something wrong. Usually just because, in a disease like COVID, you get a new strain that comes in and then that changes everything, or. Okay, so this is straightforward, right? Yeah, of course it is. Except that it isn't, right? Not for epidemic models. And the key reason for that is this likelihood function that I talked about yesterday for compartmental models relies on having exact observations of not only when events happen, but also what type of event they are, okay? So if you think about your Gillespie simulation algorithm, yeah? You simulate a time to the next event, you simulate the event, and then you update the rates, and then you carry those forwards, right? So the model itself depends on, so let's take a simple SIR model as an example. The model dynamics depend on knowing the number of infectives and the number of removals, and exactly when those events happen, all right? But we don't observe that. I mean, I've never seen a real-world data set where we observe exactly those things, right? We might, for example, observe number of deaths, okay? And that could be a proxy for the number of removals, but that still leaves us with the number of infectives, and how do we calculate that, right? And so if we don't have the right measurements, then we actually can't write down a likelihood, okay? So the likelihood becomes intractable, and this becomes what's called a doubly intractable problem, okay? And there's lots of reasons why we don't observe this. So, I mean, there's things like surveillance. Surveillance is often biased. We often have underreporting, imperfect coverage. We might have misdiagnoses of conditions. We might have false positives and false negatives of a diagnostic test. There's lots of reasons why what we're observing is not an exact map to this. We also often have rounding error, okay? So many data sets, particularly in real time, might be rounded to the nearest week or the nearest day. They're not exact. And there may also just be some components of your epidemiological model that are just never recorded, okay? So for example, if I was feeling sick from COVID, then I would probably be able to tell you roughly when I started to feel sick. But when I started to feel sick is not when I was infected, right? I was infected at some time point in the past, and I have no idea when I was infected. So those, and yet the dynamics of my model require that I know those things, okay? So the really difficult thing with epidemic models is not per se the model, it's much more to do with the fact that the data are not collected at the same scale as your model is defined, okay? And this is the real headache from a methodological perspective. And I will preface this with dealing with these challenges is hard, okay? We'll have a go at this, and you can play around in the practical with some of the ideas I'll talk about later on, but this is not a click a button and get a result type problem anymore, okay? Unfortunately, there are very few software packages that are general purpose enough to allow you to fit any type of model that you would want at the moment, all right, using these kinds of techniques. So it is a difficult area. Okay, so I promise that there's not too much maths in this, okay, but I'm going to just introduce this at least conceptually, okay? So what we have is essentially a large-scale missing, not at random problem, okay? So we have a bunch of missing data, and in order to deal with that, we need a model. But fortunately, we do have a model, right? We have our whatever model we're building, our SIR model, or SEIR model, whatever. And so one approach, at least from a probabilistic perspective, is to use what we call latent variables. And when I talk about latent variables here, I don't mean latent as in the incubation period of a disease. What I mean is latent as in unobserved, all right? And as yesterday, I'm going to use Y to denote the observed data. Okay, theta are the parameters of my model, however many of those I've got. And I'm going to introduce a set of variables x, okay? And these are going to correspond to the exact events that happen and when they happen, right? So x corresponds to what I would like to observe if I could observe everything perfectly, okay? And mathematically, at least, the likelihood function, remember the likelihood function is a function of the observed data, okay? So it is the conditional distribution of the observed data y given the parameters, okay? X does not appear in the left-hand side, okay? But what we can do, using probability theory, is we can write our likelihood in this form, okay? So we introduce, effectively what we do is we introduce our hidden variables and then we integrate them out, okay? And so in this circumstance, what we actually have is we have a probability distribution for the hidden states, okay? So this is in fact, the likelihood that we talked about yesterday, right? So if I observe everything, exactly when events happen, exactly what they are, then this would be the likelihood, okay? And that follows the same form as you would use for the Gillespie algorithm, right? So it becomes a product of exponentials. But then what I have is I have some other process here which is conditional on the hidden states. So this distribution is basically saying, how do I map my unobserved true number of infectives and removals to what I observe in the data, okay? And this is what we tend to call an observation process, okay? So we have an epidemic process and an observation process. Now, the form of this will depend on what your data is. So if, for example, your data are diagnostic tests, then this might be a function of the sensitivity and specificity of the tests, okay, given the true status, okay? And the idea is that if we could do this integral, then effectively we are averaging over all possible epidemic curves that we see that are consistent with our data, okay? And what this does is it means that we can actually write down a form for this, okay? The problem, as you're probably getting the hang of now with most of these kind of statistical methods, is that we can't do this integral analytically, okay? And so if we can't do this analytically, what good is it to us, right? But actually, what we are going to do and what you can do is, if for any of you that haven't blanked out yesterday's lectures entirely, and I wouldn't blame you if you did, this is an expectation, right? It is the expected value of this observation process given that my x's are sampled from my model or simulated from my model, okay? And yesterday we spent quite a lot of time talking about how we can estimate expectations by using numerical techniques like Monte Carlo integration, okay? And so hopefully it won't be a massive leap to kind of think, okay, can we apply the same kind of ideas here? So instead of calculating this exactly, could I approximate it, okay? And it turns out, yes, you can. So, oh, sorry, one more point I should make about this, just to hammer this home even more. Often, we don't even know how many missing data points we've got, all right? So if you imagine an epidemic where I see 10 deaths, well, that means there must have been at least 10 infections, but there could have been 11, there could have been 12, there could have been 13, right? I don't know. And if I change the number of infections, I change the number of variables I have to integrate over. So this integral is even what we call a trans-dimensional integral. It's horrible. But we can simulate from our model, and if we can simulate from our model, then we can potentially deal with this, okay? So there's two approaches to dealing with this. I'm just going to give you one very quick slide just to raise this. Andrew, close your ears. So one technique for doing this, if you are a Bayesian, is that you can, instead of writing an MCMC algorithm that estimates just the parameters, you can write an MCMC algorithm that estimates both the parameters and the hidden data, okay? And then, once you've done that, you can just ignore all the x parameters and take the parameters and that will give you an estimate of the posterior distribution, okay? And this approach is called data-augmented MCMC. And it is incredibly powerful, okay? But it is very hard to implement, okay? It's hard to implement, it's hard to optimize, it's hard to code, and it's hard to scale up, okay? So if you're interested, I've put a load of references in here. The initial papers that started to do this were Gibson and Renshaw and Phil O'Neill and Gareth Roberts. Chris Jewell has a nice paper looking at doing this for foot and mouth disease in a big spatial model, okay? It is super flexible. It's just really, really hard to use, okay? And you have to, you essentially have to have a degree in statistics to even begin thinking about this. It's not straightforward, but it is really good. And if you're very comfortable with this, you could look at those papers and they're great. What we're going to do here is we're going to use an alternative approach, okay? And this is really, I'm not arguing necessarily that this is a better approach, but it's closer to the sorts of things that you guys have learned in this course, right? So hopefully it will tie together some of this stuff. So instead of estimating the x's, what we're going to do instead is build an inference algorithm where we just simulate those x's. We simulate from our model, okay? And then we're going to build an inference algorithm that basically utilizes simulations to approximate our likelihood function. Okay? And there are lots of advantages to these kinds of methods. Okay? They're often much more memory efficient. They're often straightforward to parallelize, right? So if you have a high-performance computing system, you can run them all in parallel, so it can become much faster. But one of the key points is that simulation is often a lot easier than doing data augmentation, okay? You guys have already come across the Gillespie algorithm, and the Gillespie algorithm, at least in theory, can be used to simulate pretty much any epidemic, okay? It will be slow for a large epidemic, and there are ways of speeding this up, but it works, okay? So it's not overly difficult to simulate from these models. And so the idea is that these simulation-based algorithms will typically take your simulation model and plug it in to the inference algorithm, and then you run the inference algorithm, and then it does its thing, and it simulates from the model, and then it throws out some results, okay? So sometimes these are called plug-and-play algorithms. I don't like that because it infers that you don't have to think about what you're doing, but, okay? But there are some practical difficulties. And I'm not going to go into those because I'm just going to show you particle MCMC. But there are some practical difficulties with it as well, so this is not a golden bullet. If any of you are interested, there is a whole list of good papers looking at a whole range of different statistical inference methods. And they're all linked and they're all at the end of the slides, okay? If you don't want to be Bayesian, then the thing to look at is the maximum likelihood via iterated filtering algorithm. This is Eddie Onadi's algorithm. This is implemented in the package POMP in R, okay? This effectively tries to do the same thing we're doing here. It tries to use simulation to, in some sense, average over the hidden states, but it's aiming at a maximum likelihood estimate. It's not aiming at a posterior distribution. What we're going to look at today is this particular method, Particle MCMC. But I just wanted you to be aware that there are lots of approaches, and this is just one of them, okay? And I chose this one because I think it would be the easiest to kind of illustrate the ideas based on what you already know from the course. Okay, so in order to understand particle MCMC, we have to understand something called pseudo-marginal MCMC. And this is, ignore the name, okay? It's not as complicated as it sounds. Pseudo-marginal MCMC, if you recognize this from yesterday, okay, this is the Metropolis-Hastings algorithm, yeah, that we looked at, we spent lecture 3 looking at, okay? Now, if you remember, the Metropolis-Hastings algorithm required that I can write down the likelihood, okay? But I've already told you that I can't do that. But if it was possible to estimate the likelihood, then what would happen if I just plugged the estimate in? So instead of plugging the true likelihood in, I just plug my estimate in, okay? That's all pseudo-marginal MCMC is. It says if you can't calculate the likelihood, you can plug an estimate in, okay? And there are two conditions. As long as that estimate is unbiased and it is greater than 0, it is positive, then this algorithm will converge to the true posterior. Okay? So even though you are estimating the likelihood, if you run your MCMC for long enough, it will give you the right answer. Okay? And this is a remarkable piece of theory that I still sort of look at it and go, really? Is that true? Oh, thank you. But it is true. Okay? So many approaches are now looking at saying, okay, can I generate unbiased and positive estimates of the likelihood in an efficient way? And if I can, then I can plug that into an algorithm like this, and then I solve my problem, right? So, how do we estimate likelihoods? Well, as I just said a few slides ago, the likelihood, as long as we choose this form here, okay, is an expectation. And so if it's an expectation, we can use the law of the unconscious statistician, and we can basically say, okay, if I simulate a really large number of times from my model, and then for each of those simulations, I calculate the probability density function for the observation process, given the hidden states, and then I take the sample mean of those, then that is an unbiased and consistent estimator of the likelihood. Okay? So I don't have to do a bunch of complicated mathematics that I can't do anyway. Okay? All I need to be able to do is simulate from my model and write down a density function for my observation process, which is usually, Poisson or binomial or whatever, depending on what your data are. Okay? And so this is a Monte Carlo estimate of the likelihood, and it has all the properties we want. So in theory, we can just plug this in, this estimate, into our MCMC, and then the MCMC will converge to the right distribution, right? Which is beautiful. Of course, it's never that easy. That's working. Okay. There is a little catch. Okay. Remember that yesterday we talked about the convergence and the mixing of the MCMC chain. Do you remember that? Yeah? So what we want is a chain that moves around the parameter space efficiently so that we don't have to run millions and millions of iterations. Okay? Now, in the pseudo-marginal approach, whereas I talked to you about it before, I said, well, the efficiency depends on the proposal distribution. Okay? If I add too much noise, I reject too many things, and if I add too little noise, I don't move far enough. Okay? In a pseudo-marginal algorithm, in addition to that, you also have that the variance of the estimator of our likelihood also has an impact on how well the chain mixes. Okay? So if my estimator is not very good and it has a large variance, I'm very uncertain, then the mixing will be small here, or be poor, all right? If the variance is very small, then the mixing will be much better, okay? And if I were to take an infinite number of simulations of my model, then I would get the exact likelihood, right? And then the only thing I would need to worry about is the proposal distribution, okay? So if we do pseudo-marginal MCMC, we also need to think about the variance of this estimator, okay? And generally, to reduce the variance, in a Monte Carlo scheme, don't know if you remember yesterday, we saw that graph where the Monte Carlo variance gets smaller as the number of samples gets bigger, okay? So in order to make the variance smaller, we just need to up the number of simulations, all right? But if we have a very slow simulation model, then that's starting to become very computationally intensive, right? If I have to run 100,000 iterations of my MCMC and then I have to run 1,000 simulations for each of those, then it's starting to get very slow. So the other option you've got is to actually improve the estimator. Rather than using this naive Monte Carlo estimator, we could use a better estimator which still has the same properties but has a lower variance. And so it's really this idea that led on to something that we now call particle MCMC, okay? And that was first published in this really nice paper in Journal of Royal Statistical Society by Christoph Andrew and colleagues in 2010. Okay, so it's not a particularly old approach. And what it aims to do is to use a technique called sequential Monte Carlo in order to produce an unbiased estimate of the likelihood that has a lower variance than if we just did this very simple Monte Carlo approach. Okay? But if you ever hear particle MCMC, again, it's becoming increasingly more used in the literature. This is just a special case of this more generic pseudo-marginal approach. And there are lots of ways of building a particle filter, okay? But probably the simplest is something called a bootstrap particle filter, and that's what I'm going to talk you through today, okay? And how this works. So, the way that the particle filter works, it's still a simulation approach, okay? But what you do is instead of, let's say I want to do 100 simulations of my model, okay? Rather than doing them one at a time, what I do is I set up what's called a set of particles. So if you imagine that I have m, I'm looking for m realizations of my model, okay? And x naught here corresponds to the initial conditions for that simulation, right? So I could start them all with a single infective at the beginning, or I could do whatever I like. So I start off with 100 sets of initial conditions, and each one of these sets is what we call a particle, okay? So when I talk about particles, just think about that as a realization, okay? Or in this case, a partial realization. Because the key thing is that in particle filtering, what you don't do, you don't simulate the entire trajectory. You don't simulate from time 0 to time t, okay? You simulate one time step at a time, okay? So each particle, you update that particle by simulating one time step forwards, yeah? And this is a stochastic simulation, so each particle, even if you start them in the same place, will have some variability, right? Because it's a stochastic algorithm. Now at this point, you then have this additional step where you give each of those particles a weight. And the weight is determined by the observation process for the observed data y at that time point, given the hidden states from that particular particle. Okay? So each weight is given a probability density, and those weights are going to be higher for a trajectory that is closer to the data, yeah, that is more consistent with the data. And then what you do is you normalize those, and you do what's called a resampling step. So if I take my 100 particles, if I take my first particle, what I do is rather than just simulating forwards another time step, I take a random sample from my 100 particles, okay, where they all have a slightly different weight, okay? So particles with a higher weight are more likely to be sampled than particles with a low weight, okay? And then I propagate that particle forwards instead, okay? And then I continue this process. So I've got a schematic to kind of hopefully make this a bit clearer, okay? So here we've got a time series over time, okay? And I'm going to set up a bunch of particles at time 0, okay? And here I've got some distribution that sets my initial conditions so they're not all the same. And what I do is I simulate forwards each of these particles one time step, okay? And you imagine that maybe this is number of deaths or something that I want to calibrate to, okay? So I simulate forwards, and then I compare these things to the data, okay? So imagine that I now have a data point. So my data point here is given by this red dot, okay? So this has 2 deaths at this point, okay? And then I have some observation process around that data point. And so for each of these particles, so this is my probability density function for y given x, and you can see that things have a higher weight if they're closer, and they have a lower weight if they're further away. Okay? So each of these particles gets a weight. So you can't see it particularly well here, but it's a bit better in some of the later examples. But these particles here have a much higher weight than these particles here, right? I've scaled the size of the dot. So then what I do is I do this resampling step. And it's a resampling with replacement, which is why it's called a bootstrap particle filter. So when I do the resampling, there are some particles like this one here that doesn't get sampled at all and doesn't get propagated forward, okay? Other ones, like the ones down here, get sampled multiple times and they get propagated forward more than one time, okay? So I choose whichever particle it is and then I simulate them forwards, okay? And then I continue to do this. So now at time point 2, I have another data point, all right? So now my data point is here. So then I reweight them. Now these particles have low weight because they're far away from the data. These ones get resampled, okay, propagated forwards. Then I compare them to the data. Then they get reweighted, and then they get propagated forwards, and so on, okay? So what the filter is actually doing is it's, rather than simulating the entire trajectory in one go, it's simulating time steps, one time step at a time, and then it's placing a greater weight on propagating forwards trajectories that are closer to the data, okay? So this is a really neat idea. I thought it was a really neat idea. The immediate thing that I thought about this, though, is, but surely we're just biasing, right? Because we're just selecting the ones that are good. But actually, that's not strictly true. We are selecting the ones that are good, but we're not doing that deterministically. Because we're doing this resampling step, it turns out that you can still generate an unbiased estimate of the likelihood, even if you use this type of scheme. So it's a slightly different estimate. And it looks a bit like this, but it basically becomes a product over all the different observation errors over your time course, okay, your time series. But what's neat about this is that this estimate is much more efficient. It has a much lower variance than the Monte Carlo estimate. So I will get a much better estimator for the same computational output as I would do if I just simulated the entire trajectory and then compared it to the data. Okay. So this is really the idea. And so because this is unbiased and positive, I can just plug this into an MCMC algorithm and it should converge to the correct posterior distribution. And the advantage from the perspective of what we've been talking about in this course is that you only need a simulation model, which we already have, and you need an observation process, some sort of observation error, which you can specify. And there are lots of extensions to this, but this is probably the simplest one. Okay? So just to show you how this works, I'm now going to take a case study of influenza in a boarding school. I'm realizing that our slides seem to have a lot of boarding school stuff in them, given that neither of us went to boarding school, but anyway. So these are actually data from a British Medical Journal case report from the 1970s. And the data are provided in this outbreaks package. But what this is an outbreak of flu, okay? And what I'm just going to focus on here is the number of individuals in bed, okay, which were recorded. And you can see that it has the classic epidemic curve over time, where the number of individuals... So essentially, when an individual showed clinical signs of sickness, they would move that individual into a hospital wing, okay, which is what they mean by in bed, okay, and then they convalesce there. Now, the model we're going to fit to these data is an SIR model, okay, but with an additional removal compartment. I'm trying to remember off the top of my head what that's for, and I can't, so it'll come back to me in a minute. So this is our underlying model, okay? And we can simulate from this model, right, using something like the Gillespie algorithm. What we also need, though, is some sort of error process, observation error process, around our observed data. And we're going to fit... oh, no, so I know what this is. Okay. So what happens here is... So in this particular case, this is a slightly bizarre data set. What they do is they move people into hospital, into the hospital wing, which they assume is the removed class because they're not transmitting anymore because they've been isolated from the rest of the school. But then at some time point later on, they move them away from the hospital wing to convalesce, okay? So this is an R curve, but in all other R curves you've seen, the R curve asymptotes, right? It's always increasing. But this one, individuals can leave the R class to move into this convalescence class. So you've got this sort of slightly weird behavior, okay? So we're modeling this here by having an R class and then having a movement from the R class to this convalescent state, okay? That's what we're doing. So the data we have, what I'm going to do, and again, I am not 100% convinced. This is something that people do a lot in the literature. I'm not convinced that a Poisson distribution is exactly the right thing to do, but we're going to do it anyway. What we're going to assume is that our observed number of removals at any time point t, so the number in bed here, is going to be drawn from a Poisson distribution with a mean equal to the true number, okay? Where the true number here is the number that we simulate from our model, okay? And we're going to add a little tiny bit of error here. Can anybody think of why we might do that? Add a small positive constant here. Stochastic model. So this is the mean or the rate of a Poisson distribution, and rates cannot be zero, right? But in our stochastic model, it's perfectly possible for us to have a time point where we have no people in hospital, in the removed class or in bed. So this tiny, tiny constant is just added to basically make sure that that works. The initial population size is 763 pupils, and we're going to assume an initial introduction of a single infective child at day 0, okay? So in this model, this is an example of what I was saying about the fact that the data we have don't correspond to the, we have no information on when individuals become infected. We only have information on when individuals get moved into bed, okay? So when they get removed from the population. So if we wanted to fit this model, we would need to have a way of estimating all of the hidden information, i.e. the infection times. And so that's what we're going to do using Particle MCMC, okay? If you're interested in this, Seb Funk has a nice paper, or a couple of nice papers, that uses this kind of approach. And Aaron King, also in the POMP package, has this. So what I did was literally run that Particle MCMC algorithm I told you about on the last page. I ran the MCMC for 100,000 iterations, okay? Again, once you've got the Particle MCMC running, the rest of it just falls out like a standard Bayesian analysis, right? So I look, I see when my model's converged, I throw away the burn-in. So here I've thrown away 20,000 samples, and I've used 75 particles for the particle filter, okay? So each of these estimates is derived from 75 particles. And you can see that this converges and mixes nicely, okay, for the 3 parameters, beta, gamma, and gamma 1. I can do all the usual stuff. I can map these out, so I can give you a posterior distribution for each of these 3 parameters. I can generate point estimates, which I've done with the posterior mean here. And I've generated a 95% credible interval for each of these as well, okay? And the beauty of the pseudo-marginal algorithm is it says, well, we know that this is an estimate of the exact posterior distribution, okay? There's no approximation coming in here outside of how long you run the MCMC for. Okay. So that's the last thing I wanted to say, okay, just on this as a method. It is a powerful approach for inference for partially observed systems, okay? If you want to learn a bit more about pseudo-marginal methods, Darren Wilkinson has a couple of blog articles which I thought were excellent. They're often used when you have to have some kind of stochastic discrepancy observation process. Okay, so you have to have a stochastic model and a stochastic observation process. And there are other types of particle filter that exist. One word of warning, though. I actually went to the Royal Statistical Society and saw the Christophe Andrieux's paper being presented. And at the time, the way that the Royal Statistical Society works with red papers is that they ask people in the audience to stand up and make comments. And one of the comments that came out, which ended up in the paper itself, is that this method is computationally brutal. Okay? So it is tractable. We can code it up. But what we are doing here is lots of particles, lots of simulations across lots of iterations of our MCMC, okay? So for very simple models, it will run very quickly. But if you have a really complicated model, those simulations take a long time to run, and you have to run a large number of particles, it is slow, okay? So as I said before, there isn't a golden bullet for any of these things. In the practical session this afternoon, if you choose to do the Particle MCMC one, I've written some code that will do this. So you can specify your model in the same sort of way that you specify a SimInf model. And then you specify an observation process, and then it does all the dirty work and runs the particles of MCMC and does all of that for you, right? It is not... I take no warranty on the package. It was designed really for teaching this course so that you guys can have a play and get your hands dirty and sort of have a feel for what the algorithms do, okay? But it should work fine, and so hopefully you can get something out of it. There are some software packages that will fit these sorts of models. POMP is quite a common one, and that's the one that has, these are all R packages. Simbid is the package that I wrote, so that's going to be what you guys are using. SimInf, obviously you've already come across for doing simulations. SimInf doesn't include particle filtering at the moment, but it does include something called approximate Bayesian computation, which we don't have time to cover. Nimble, we introduced yesterday. Again, Nimble will do particle filtering. It's another R package. It's a generic Bayesian package. I've not used it to do particle filtering, so I'm not quite sure how good it is at it, but it is a good package. And if any of you are interested and you have really super computationally intensive models, then we also have a package called HMER, which does something called history matching with emulation, which I do not have enough time to go into here, but it's specifically designed for when your simulation models are ludicrously computationally expensive. Okay, bunch of references. Thank you. You got to the end. Does anyone have any questions? No? Okay, yep.
There's a part where you use the Poisson distribution.
Yes.
Why?
Right, so that is because in order for this to work, you need some kind of error distribution that says, so what we're assuming in this model, well, okay, not technically.
The question is why Poisson?
Why Poisson, okay.
Why not binomial? Because or another distribution.
People use the Poisson because it's got one parameter to estimate, and it approximates a count. It's the simplest count process, which is just one parameter. The thing that it gets wrong, and the reason not to use it, or my reason, T.J might have a different reason. I think he was thinking of something else, maybe why he doesn't like using it. But the reason a lot of people don't use it is because the Poisson has a very specific relationship between the mean of the process and the variance. So the mean is equal to the variance for a Poisson process. Most epidemiological data is over dispersed, and that's why typically we use a negative binomial distribution, which gives you a shape parameter. So it's a bit like the gamma distribution, but for count data. Did you throw something?
No.
No, I got away with that one. Okay.
I'll let you off.
Yeah, it's a phenomenological model, but you're spending that extra parameter. And if you're already struggling to pick your model, you might use a Poisson just because it's expedience.
But what I would say, so one of the reasons why they choose a Poisson in particular is because it does have the property that the variance scales with the mean. And for a lot of these epidemic models, if you remember those stochastic models, as the counts increase, the variance tends to increase. So it has that basic property, but as Andrew said, it's also tends to be, the negative binomial can allow you to have more variability than the Poisson if you want to. So that is definitely a choice you can make. The binomial question really comes down to, so binomial is very useful if you want to do something like underreporting, because with underreporting, you know that there's a systematic bias. Right, you know that what you're observing is less than what's actually happening. So if you did that, you could have something like a binomial distribution where n is the true count and p is the proportion of those observations which you actually observe. So therefore, what you would always have is a higher true curve than your observed curve because you've incorporated that under reporting. So that's a way that you could use the binomial. There is a slight sting in the tail. So the other reason why people choose Poisson is because of a pragmatic reason. So if one of the issues you've got is in particle filtering is something called particle degradation, which says that sometimes those particles can have zero weight. So if you imagine your binomial distribution, if my binomial distribution, if my true value is lower than my observed value, and I have underreporting, that can't happen, right? So the probability, because your observation model is saying, well, the observation has to be less than this. It can't be more than this. So in that circumstance, that would have a zero weight, right? Because that observation process is not valid. Now, zero weights are not a problem on their own, but they can become a problem if all of your particles have zero weight. Because then your particle filter dies a death, doesn't complete, okay? The Poisson never has that problem because you can have things less or greater than. So I think it's personally something that tends to be chosen out of convenience. And again, for a lot of these large-scale models, there's an element where they are trying to get something useful working, and sometimes you just have to make a pragmatic choice. There are some more technical stuff, but I won't go into it about why you could think about Poisson as not being particularly good. But it is a choice that you make, and it might be very different if you have a different model. Okay? Or you could consider something like the negative binomial, which would allow you to have more variation, or even less variation, depending on what those parameters are. So yeah, that's one.
And a lot of the time, the data which we're fitting to is case count data, in that we don't know what the reporting correction is. And others, I'm not sure how common it is, but if you have a longitudinal cross-sectional data, so if you say testing the population, and it is literally a proportion, you've got a choice as to whether to model that as a count or a proportion. It would always be more natural to model it as a proportion. And this is where T.J might start throwing things, I'm not sure. The likelihood, a binomial likelihood, is going to be much more pointy than one where you're modeling counts, because it's a lot more informative when you've got a fixed sample size. Now that can be great, it can make your model converge, but particularly for this type of model, that could actually increase your chance of particle degradation, because you're going to be throwing away particles because the likelihood is so informative. Sometimes a very informative likelihood actually works against you in terms of fitting your model. So using a more dispersed and flexible distribution can just help. On the flip side, if you let your dispersion parameter just range completely, without being lazy and putting strict prior on it, a very good way of fitting any data set is just to have a completely flat observation process, so you just get random values. So a lot of the approximate methods, which are more approximate than TJ's talking here, where you make some assumption about reporting, it's a very judicious balancing point between making the likelihood you choose, the observation process, flexible enough that you get some information from the time series, but not so flexible enough that the method just gets stuck and crashes.
Because the key thing about the simulation methods, and one of the when I said that there were additional difficulties, one of those is the fact that when you simulate from the model, there is no guarantee that a finite number of simulations is going to be anywhere near to your data, right? Because these are stochastic models. Something like data augmented MCMC circumvents that because it only simulates the hidden states conditional on being consistent with the data. So it doesn't suffer with the same problem, but that comes at a cost that it's a very difficult algorithm to code up. So all of these things are balances. which is why at the beginning of all of this I said, you know, we don't have a perfect gold standard, simple to introduce way of doing this for all models. There's lots of approaches in the literature. They all have different trade-offs. And unfortunately, that's where we're at the moment. It's a considerable statistical challenge. But there are really good people working on it. So it will get better. But it might, you know, just take a while. So the other thing that people will do often is simplify the model. So this is only really relevant if you really want to fit your SIR model in this way. If you're prepared to make some simplifying assumptions, or you know, if you want to estimate R0 by the, you know, the different methods we looked at yesterday, you can do that as well. And sometimes you can simplify your model down so you're doing, again, approximate. You can build an approximate model that has a tractable likelihood as well. So there are different things you can do. But again, there's just not a very easy, I click a button and I get a result. Okay, all of this stuff needs thinking about and tweaking, and yeah. Yeah, Isaac.
Thanks, for these methods that have been introduced. Two things. The first one is computational intensive, which is quite scary, given what we already know in terms of the computational cost. This is brutal. I'm quite scared and worried why I would need to invest so much time in the brutal.
Well, it depends on your model, right? So in the practical, you will see that you can get this model running. I mean, it's not lightning fast, but it's also not horrible, right? You're not talking hours and hours and hours, you're talking minutes, okay? However, if you have, so for example, for the COVID work we were doing, we had a particle filter that was only simulating over between sort of 30 and 50 days. But this was a big meta-population model across the whole of the UK where we were moving, you know, literally moving commuters between different regions. There was a lot going on in the model. Those particle filters took anywhere from 3 hours to run a single run to 15 hours, depending on where you were in the particle space. So that is clearly something for which you could never embed that within an MCMC algorithm. It wouldn't work. And that's why if you have a model that's that computationally intensive, then you need to use a better method. Well, not a better method, but an alternative method. All the alternative methods work in slightly different ways, though. So again, there's trade-offs with what you do. But you know, depending on how large your system is, this can work very well. And this has been used for modeling Ebola outbreaks. It's been used for modeling all sorts of things. So it does work well. But you might be thinking about a day's worth of runtime. And I would probably argue that for most of the stuff I do, a day's runtime is minimal in comparison to the months and months and months you spend collecting the data, building the models, and you know. So all of these things are relative, but what it isn't is a click and get an answer immediately. Okay, that's the key thing.
Maybe the last one.
Yeah.
Thanks. To maybe we've been working with this, but you're very comfortable.
What's this?
You're very comfortable. How much time does it take for someone to be comfortable?
Yeah. So my short answer to that is if you're not very comfortable with tedious statistics, then you should probably try and do it in one of these packages that exist, as long as you can get it to work in those packages. So if you have time series data, things like POMP will work really well. The SymBib package that you'll look at today should work pretty well. I've not had any problems with it. You know, so yeah, it is definitely not something that I would consider that you would want to code up yourself, unless you were very comfortable with MCMC. I mean, ultimately.
However, this algorithm, so although it's computationally brutal, what is its saving grace is that it's relatively simple to code up compared to the gold standard, which would be data augmented MCMC, which is a nightmare. So there's often a trade-off. There's a trade-off in everything we do, actually, in terms of how much time we want to invest ourselves, human thinking time and human coding time, and how much time we're willing to just let a computer run for us. So I think that's actually the beauty of this sort of practical MCMC method, in that it's relatively simple to code that up. It just depends on simulating your model. That's straightforward, but the cost is you might have to run it for Well, maybe that's okay because you haven't spent a year of your life debugging a program to do data augmented.
That's a really good point. And I mean, this is the bootstrap particle filter, right? It's 4 steps. So as long as you can do the simulation bit here, which you know how to do, right? And as long as you can generate whatever your observation, this is it. It's 4 steps. And then you're embedding that in Metropolis Hastings algorithm, which is another 4-step algorithm.
Yeah.
So it's not that difficult. What I would say, though, is usually most of these things, if you coded this in R, expect your runtime to go through the roof, because it's effectively a double loop, right? So every iteration you're looping over this, and then you're looping over this multiple time points. So most of these packages, what they do is they turn it, like SimInf does, they turn your model into C code, they compile it, and then it's fast, okay? But Andrew's right, it's a 4-step algorithm for the particle filter, and it's a 4-step algorithm of Metropolis Hastings, so you could do it yourself, and it's not too onerous. It really depends on how difficult this thing is. What I would say, though, sorry, just one more point on that, is if you do read the particle filtering literature, just be warned that you really need to know measure theory to understand any of it, and I don't understand measure theory. So there were a couple of so Darren Wilkinson's blog was the thing that actually put this in a simple way that I could understand in order for me to get my head around it. It is, the particle filtering literature is not nicely written unless you are a probability theorist. So I will just pre-warn you of that one. Yes?
I was wondering, are you able to apply space partitioning?
What's that, sorry?
I was wondering whether you're able to apply the space partitioning or parallelization on those particles.
You mean parallelized particles? Yes, you can. You absolutely can. But the bit that you would have to parallelize is, so you can't parallelize the whole algorithm because you've got this resampling step. But what you could do is parallelize this bit. So once you've chosen the particle, you can parallelize all of your particle. You can run each of those particles in parallel because they don't interact with each other, right? So running from 1 to m of your simulation can be done in parallel, but then you have to, because you have to weight them all and then do the resampling, that can't be done in parallel. So yeah, you can parallelize parts of the algorithm, but not the whole algorithm. Similar idea, by the way, is used in likelihood-based inference. If you've got a very, very complicated likelihood function, often people will parallelize the computation of the likelihood just to speed it up as well. Yeah. Whereas if you did Monte Carlo estimation, you could parallelize everything. But it isn't going to be as good as this. So, yeah. Okay. Anyone have any final questions? Okay. Right, well, thank you very much for your attention. And we have a practical now. Did you? Or we probably have break or something. I've lost track of time.
It's basically lunchtime. I think, sadly,